So let's talk about conditional statements. Conditional statements are just if-then statements. If this happens, then this happens. If I do this, then that happens. But statements are not always written in that form. Sometimes you have to rewrite them. Here's an example. Let's say I don't really like the cafeteria food, but I love lasagna day. So I buy lunch in the cafeteria on days that they serve lasagna. Here's one way that you could rewrite that. If the cafeteria serves lasagna, then I buy lunch. Here's another example. Water freezes when the temperature is below 32 degrees. So to make that an if-then statement, you'd write, if the temperature is below 32 degrees, then the water freezes. Now, just because I make an if-then statement doesn't mean it's true. Let's evaluate the validity of a few statements. The word valid just means true, so we're just trying to figure out, are these statements true? Here's the first one. If you live in Garland, then you were born in Texas. What do you think? Well, this one's false because maybe you live in Garland, but you were actually born in New York. I have a friend named Mrs. Smith, and she actually was born in New York, but she lives in Garland. So Mrs. Smith is a counterexample for this. She's an example that I can use to prove this statement's false. For a counterexample to work, the first part of the statement, what we call the hypothesis, needs to be true. So Miss Smith, she lives in Garland. Then the second part needs to be false. This part's called the conclusion. So Miss Smith was not born in Texas, she was born in New York. So if the if part is true, for an example, and the then part is false, then that is a good counterexample that you can use to disprove that statement. So Miss Smith lives in Garland, but she was not born in Texas, so she is a counterexample. Let's look at the next one. If a shape is a triangle, then it has three sides. Yep, this one's true. That's the definition of a triangle. If x is an odd number, then x is divisible by 3. Can you think of any odd numbers that are not divisible by 3? I can. And if you can think of just one, that's enough to prove this is false. Here's one number that's odd, that's not divisible by 3. 5. It's true that 5 is odd. It's false that 5 is divisible by 3. If you can think of just one counterexample to a statement, then that statement is false. It has to be true all the time to be true. If it's false even once, then it's a false statement. We can't count on that statement. Okay, how about this? If you are 15 years old, then you are a teenager. Yes, this is true. 15 has teen in it, right? Anybody who's 13 to 19 is a teenager because they are 13, 14, 15, 16, 17, 18, or 19. So that's a true statement. We're not going to try to disprove true statements. So I don't need to generate a counterexample when my statement is true. Okay, so that's how we can evaluate the validity of a statement. We look for a counterexample and see if we can prove it's false. Now let's talk about related conditional statements. So here's my statement. It says, if the measure of angle ABC is 90 degrees, then angle ABC is a right angle. So this is a true statement because that's the definition of a right angle. A right angle is just an angle that measures 90 degrees. And I can write related conditional statements for this statement. One of those would be the converse. So for the converse, what I do is interchange my hypothesis and my conclusion. So remember, the iffy part of my statement is called the hypothesis, and the then part is called the conclusion. So what I've done right here is I've switched them around. I interchanged them. So now the conclusion is in front and the hypothesis is at the end. I just switched them, right? That's called the converse when you switch those. Let's see, is it still true? Is the converse true? If angle ABC is a right angle, then angle ABC is 90 degrees. Yep, this is still true. Okay, the inverse is actually just like the original statement, except that you add a keyword in two places. You add the word not. So now we say if angle ABC is not 90 degrees, then it is not a right angle. That's the inverse. We're negating both the hypothesis and the conclusion. And in this case, this is true again. So we have another true statement here. Our converse and our inverse and our original statement are true. Now let's talk about the contrapositive. And to write your contrapositive, what you're going to do is interchange the hypothesis and the conclusion of the inverse. So we still have our nots. And this time we say if ABC is not a right angle, then it's not 90 degrees. See how we did that? And this one happens to be true as well. So in red here, I've written the steps that you use to write the converse, inverse, and contrapositive of a conditional statement. To write the converse, you interchange, that means switch, the hypothesis and conclusion. To write the inverse, you negate the hypothesis and conclusion, which usually involves writing the word not, like we did here. And then for the contrapositive, you both interchange and negate the hypothesis and conclusion. So we switched them and we added the word not. So that's how we write our statements. I also want to talk with you just a little bit about biconditionals. To write the biconditional of a conditional statement, start by writing the converse. So our original statement said, if 2 points lie on the same line, then they are collinear. And this is true because this is the definition of collinear. It's just 2 points on the same line, right? Or more than 2 points in the same line can also be collinear. So our converse says, if 2 points are collinear, then they lie on the same line. And this is also true for the exact same reason. That's the definition of collinear. Now, the biconditional puts these two statements together. We say 2 points are collinear if and only if they lie on the same line. I like to call this my super if. If your original statement is true and its converse is true, then the biconditional is also true. And it's kind of a combined way of expressing the truth of both the converse and the original statement in just one big, powerful statement. This if and only if allows us to say that 2 points are collinear if they lay on the same line, and also that if 2 points lie on the same line, then they're collinear. It communicates everything that was in the conditional and its converse in one statement. It's very efficient. Of course, if one of these statements, either the original or the converse, were not true, then the biconditional would not be true. In order for it to be true, both the original statement and its converse must be true. Sometimes you might see this notation that has P's and Q's. It's not hard. You just need to know that the P represents the hypothesis and the Q represents the conclusion. If you know that, it's really not confusing. It's just shorthand. It lets you talk about the relationships between statements without having to write the whole statement. So let's look at an example. Here it says that P, our hypothesis, is x equals 20. And Q, our conclusion, is that 3 times the sum of x and 2 equals 66. This funny looking little squiggle here means not. So in our example here, they're using squiggle Q, arrow squiggle P, and that means if Q, which is 3 times x plus 2 equals 66, does not equal 66, then x does not equal 20. So if Q is not true, then P is not true. Let's do an example of our own here. It says if P is true, then Q is true. So let me write if P. So if x equals 20, then Q. And Q is 3 times x plus 2 equals 66. So that's if P, then Q. Let's try a different one. This says if not P, then not Q. So here we're taking P and Q and we're adding this very important word not, and that not comes because of that squiggle right there. If x does not equal 20, then 3 times x plus 2 does not equal 66. Now for this next example, we have if Q, then P. So we would say if 3 times the sum of x and 2 equals 66, that's our Q, then x equals 20. See, all we did was put our Q first and then our P. This next one has a double arrow here, and that means if and only if. So I'm going to start with P, that's x equals 20, and then I'm going to have if and only if 3 times x plus 2 equals 66. So P, if and only if Q. Pause it and see if you can write the next statement for number 15. Here it is. It's the same thing, just with P and Q interchanged. Now that we've written these statements, I bet that you could name them and how they're related to the original statement. Number 11 was our original statement. It started with our hypothesis, P, and it said if P is true, then Q is true. The next one is our inverse. It negated the hypothesis and the conclusion. Number 13 was our converse. It interchanged the conclusion and the hypothesis. And number 14 and 15 are both biconditionals, and they both say the exact same thing. The order of the conclusion and the hypothesis doesn't matter with a biconditional because of the if and only if. So which statement did we not write in these examples? Well, this exercise didn't include if Q is not true, then P is not true. That's what that one would have looked like. This exercise didn't ask us to talk about that, but that would have been the contrapositive. Now that one wasn't included here. So now you can see how P and Q is just shorthand. It lets you talk about these different kind of conditionals without necessarily having to write them out at full length.